So yeah, today we have two speakers who are going to jointly do a presentation. So the first one is Qinghua Liu, who's a PhD student of Jin at Princeton. And the second one is Dipendra Misra, who's a senior researcher at Microsoft Research. They both work a lot on reinforcement learning theory and have done some really awesome work in that domain. And in particular, today they're going to be talking about the paper Provable Rich Observation Reinforcement Learning with Combinatorial Latent States. Over to you.
Okay, thank you for the kind introduction. It's really nice to be back here. So today, Dipendra and I will together talk about our work on provable rich observation reinforcement learning with combinatorial latent states. Dipendra, could you go back one slide, please? Thank you. So this is a joint work with Dipendra, Chi, and John. Yeah. So in the original plan, Dipendra will present this work today, but he's not feeling very well. So I will do the first half and leave the second half to Dipendra. And by the way, he made all these nice slides. I really appreciate it. Could we start? Okay, so this work is about provable rich observation reinforcement learning with combinatorial latent states. So the title is very fancy. But the key idea is very clean and fundamental. It's basically about block MDP plus factored MDPs. Okay, so currently, Dipendra is playing a video showing a robot making I forgot the name of this desert. Yeah, so it's affogato. Thanks. So a robot making an affogato. Yeah, you can see after receiving the instructions from human beings, the robot can make an affogato automatically. Yeah, it's pretty fancy. So in this case, there are two key challenges. The first challenge is the observation of the robot is high-dimensional sensory data. For example, it can be raw images directly output by some cameras or sensors. And the second challenge is the underlying hidden state can be exponentially complicated because the latent state in this problem should encode the position of different objects. It should also encode like the rotation angles of different stuff. So of course there are also like some other challenges involved in this problem, like robustness, generalization, and optimization. But in this talk, we will mainly focus on these two challenges: rich observation and combinatorial latent states. Okay, thanks. So existing works have basically studied these two challenges separately. So in the first line of work, people mainly focus on reinforcement learning with rich observation or high-dimensional observation. So in this setting, people typically assume the observation is generated from a more concise latent state space, and the sample complexity derived only depends polynomially on the size of the latent space instead of the size of the observation space. So one popular model satisfying this assumption is called block MDPs. In block MDPs, the latent state space is relatively small, and the different latent states cannot emit the same observation. Next, please. The second line of works focus on problems with factored state space. This is known as factored MDPs. In factored MDP, the latent state can be encoded as an d-dimensional vector. So which means the latent state space can be exponentially large. But this setting doesn't deal with partial observability. So all states are directly observable to the agent. In factored MDPs, there is one common assumption, which says each factor has a relatively small number of parent factors, and the transition dynamics of each factor are determined by the value of its parent vectors and the current action. So the reason for making this assumption is, in general, the sample capacity for learning an arbitrary factor MDP would be 2 to the D. So in order to avoid this 2 to the D dependence, we have to pose more structure on the underlying graph. And by making this assumption, we can make the sample capacity only depend exponentially on the number of parents, kappa, instead of the ambient dimension, this D. Okay. Thanks. Okay. So let me show you an example. So in this example, this is a grid world. So we have an agent, and we also have several enemies. So an agent can move one step to a neighboring square, and an enemy can move uniformly at random to any of its neighbors. So we can view this grid. World as a block, as a factor MDP. So each square corresponds to a factor, and we can use the value of each factor to represent whether it's occupied by an enemy or by the agent or just empty. So in this example, so the kappa, the number of parents, is equal to 4 because the value of each square is only determined by its neighboring states or neighboring factors. But the ambient dimension, the total, is equal to the total number of squares, which can be much larger than 4. So in this case, the sample capacity of learning factor MDP would be like 2 to the 4 times polynomial D instead of 2 to the D. Okay. Okay, so now let me quickly summarize what we have talked about so far. So first, no prior works have studied rich observations and factor MDPs as a whole. Second, these two structures are actually quite common in real-world applications, and they often show up together. So as a result, we are motivated to study these two challenges in one piece by designing some sample-efficient algorithms. Next, please. So now let me introduce the formal problem setting we want to solve. Okay, so first, we consider infinitely large observation space and factored latent state space simultaneously. We will use capital T to denote the transition function, and this little q to denote the emission function. So this emission function is from the latent state space to the simplex over the observation space. Okay. Okay. So there are several settings. So in this setting, there are several challenges. The first one is partial observability. It is known that PoMDP is statistically hard to learn, except some special subclasses. So in order to avoid the hardness results from PoMDP literature, we need to make some further assumption on the emission structure. And basically, what we assume is block MDP. We assume the observations to be rich enough so that no two states can generate the same observation. In other words, we can directly decode the latent state from our observation. In practice, we can always make this assumption satisfied by adding more sensors or more cameras, so that our observations will be more rich and more informative. Okay, next. And the second challenge is the transition dynamics can be overly expressive. So we know in the worst case, learning a learning an MDP requires sample capacity linear in the size of the state space. So this is some classic result also already known. So without posing any constraint on the transition function, we can model any MDP as a factored MDP, and we can show the sample capacity lower bound 2 to the d is unavoidable. So we need to pose some extra structure on the problem so that we can avoid this hardness result. And what we assume is each factor only has a relatively small number of parents, as we have seen in the previous example. So this assumption is often satisfied in practice, and it can help us avoid this 2 to the d lower bound and make sample efficient learning possible. Okay, so far we have basically made 2 assumptions. First, we assume block structure, and second, we assume each latent factor has a small parent set. But it turns out these 2 assumptions are still not sufficient for sample efficient learning, because the emission function can be arbitrarily complicated. So we know the latent space. Is exponentially large. So we cannot expect to traverse all the states to learn the decoder. So we need some structure to make sure the decoder can be sample efficiently learned. Or in other words, it can generalize from the states we visit to the states we haven't visited so far. And we achieve this goal by assuming thanks. And we achieve this goal by assuming the observations are made up of items. So for example, if our entire observation is an image, you can imagine each item is just a pixel. Or in other words, if our entire observation is a sentence, each item can be a word. Okay. And we further require each item to be mapped to a parent latent state factor. So this assumption essentially guarantees each state factor can be decoded from its children items. So in this picture, you can see each patch of this image corresponds to a latent state, and this small patch of image is the items corresponding to this single latent factor. So this is some motivating examples for making this assumption. Next, please. Okay, so as we mentioned before, this assumption essentially guarantees each factor can be decoded from its children items. So we don't need to look at other items as long as we know what its children items lie in, basically. Yes, and we call this new setting factored block MDP. So is there any questions?
Yeah, like just a quick clarification question about this. So could you, like, is this the same as just saying that the emission kernel is also a factored kernel with few parents, and that's gonna be the assumption? So few parents for the transition kernel, few parents for the emission kernel, and that's the structure that we're looking at.
Yeah, exactly. It basically says the emission function is also factored. Yeah, you're right.
Actually, regarding that, is it few parents or a single parent? It seems like each xi is only generated from a single latent state. Is that correct?
Yeah, a single parent. Yeah.
Yeah. So each xi has a single parent.
Yeah, each.
Okay.
Yeah.
Okay.
So each xi represents an observation. Represents an item in the observation.
So do you assume that?
Because Yeah, like in the figure, you have two gray arrows going, it seems, to the same spot, but I guess those are different factors, actually. Yeah. Okay.
Yeah, that's a little bit. Also, do you need oh, okay. I just see it. So you don't assume finiteness of the atom space. Atom space can be arbitrarily large.
Yeah.
And you probably don't also don't need to assume like parametric form of a single emission for each atom, right?
Yeah, we don't assume that.
I mean, regarding, can you go back to one slide? I have a last question here. Regarding this figure, I think this figure is, you know, a canonical example where, you know, like people often think of in terms of structures in rich MDPs, and previously there's work on, you know, object-oriented MDPs, like from Michael Littman's group and so on. I'm not sure, like I can take this example super seriously, like in your formulation, because, you know, like all these objects are moving around, right? So then each patch, like they may, the latent state they depend on may change over time, which I don't think is fully captured by your formulation. Can you say a little bit more on that?
I think Dipendra, you want to explain this?
Nan, can I take that? Okay. So right. So I think you have raised a very important point that I want to maybe discuss a little bit more. So there are generally like two ways to think about a factor. So you can either think about a factor as tied to a location. So in this example, the factor is this location. So it's, I haven't drawn it, but there is you can imagine a location over here. And that location is made of 4 atoms or 4 pixels. And this is one factor. And this factor would satisfy the fixed parent factored MDP assumption, because what comes here is only can come from the neighboring parents. But there's another view, which is more concise, which is viewing objects as a factor. And so in that case, horse would be one factor, the tree would be another factor. And in my view, that is the right view, but that doesn't satisfy the parent assumption. And so the very factored MDP assumption is violated. And I think that's an interesting open question of how can we design these object-centric representation. Unfortunately, we can't cover that in this work.
Yeah, I think thanks for clarification. I think that's clear. Yeah.
By the way, is there too much background noise? It's like someone doing our garden. I can put myself on mute.
Yeah, I think it's okay. Yeah.
Yeah. Okay. So we call this new setting factor block MDP. Okay. Next, please. Okay. So in this presentation, we will assume the state space is layered for clean presentation. So it equals no state is reachable at 2 different time steps. And all the functions considered can depend on time steps. But for cleanness, we will not show this dependence explicitly in notations. Okay, next, please. So to proceed, we need to introduce the definition of policy cover. A policy cover is a set of policies. It basically says that if we restrict our attention to an arbitrary 2 kappa size subset of factors, then all its possible values can be sufficiently reached by some policy in the policy cover. So sorry, I cannot use my cursor. So if you look at the first inequality, so the first equation here, so basically the left-hand side is the probability of reaching a value configuration by some policy in the policy cover. And the right-hand side is the probability of reaching certain value configuration by some policy in the universal policy space. So okay, so basically it's saying for any, basically it's saying this policy cover can reach all the possible configurations for any 2-kappa set of vectors. And in this work, we also assume for any reachable configuration, it should be reached with some lower bounded probability. So this is for some technical analysis need. Okay, so with this, so with all the setups, I can now introduce the formal guarantee of this work. So under all the assumptions made previously, we can run an approximately accurate decoder, a transition model, and a policy cover for each time step using a polynomial number of samples with high probability. So here, kappa is the number of parents for each factor. And this eta mean is the minimum reaching probability in the last slides. And okay, and furthermore, we can show the algorithm is computationally efficient if we are given access to an planning oracle for factored MDPs. Oh, yeah, I think that's it for the first half. So if there is no question, Dipendra, please take over.
Thanks, Xinghua. So if there's no question, we can move into the algorithm. Right. So in this paper, we introduce an algorithm called factorial, which solves a subset of the factored MDP setting that we introduced earlier. But before we motivate the need for a new algorithm, let's think about why an existing block MDP algorithm wouldn't be able to solve this problem. So consider this thing. So forget that the state space is factored. Just treat the S and S prime as two states, and take the whole of observation and apply your favorite block MDP algorithm. And then one way to recover a factor would be to take the state and just look at the bit vector of this state. And so the problem with this naive approach is that you may recover factors, but those factors may no longer respect the transition property of the factored MDP. And so, for example, in this figure, S prime is the goal state, but S tilde is the recovered state. And so we can see that you can recover an S tilde such that the S tilde 1 is 1 if every S prime I is 1, and S tilde 1 is 0 if every S prime I is 0. So in this case, the S tilde 1, which is the recovered latent state, is dependent on d many states at the d many factors at the previous level. And so this gives you d parents, and your transition function has now exploded from having 2 parents to d many parents, and you will end up with a 2 to the power d sample complexity if you try to work with this learned abstraction. And so this is the challenge, that we want to recover the factors which obey the sparsity of the transition dynamics. And this motivates the algorithm that we propose in this paper. So this algorithm would work iteratively. So remember, as Xinghua mentioned earlier, we assume non-stationarity. So everything is a function of time: transition function, emission function, state, observation. So we can focus on solving the problem at a one time step, and then just solve it for all time step using induction hypothesis and apply union bound at the end. So for a given time step h, we will find the emission structure, which means that we will find which atoms are emitted from the same factor. And then we will use them to learn a state decoder for mapping it to the state S prime. And then we will learn the latent pattern structure and estimate the transition model T. And we will use the estimated model to then do planning and recover a policy cover. So that would be the 4 steps in the algorithm. So the algorithm is a little bit involved, and I'll try to cover the key details. But if you have any questions or want more details, I'm happy to chat in the informal session. So right, so these are the 4 steps. The first one would be identifying the latent emission structure. The second would be mapping the children atoms using a learned decoder to the value 0, 1. And the last one would be that once we have recovered the latent model, we use it for planning. So let's look at the first step. So in this first step, our goal is to partition the set of atoms into sets such that each set is a set of atoms emitted from the same factor. So in this example here, we want to show that U, V, and W are atoms emitted from S prime 1, and Z is an atom emitted from another factor. And this is equivalent to predicting if a given pair of atoms are emitted from the same factor or not. So the whole graph prediction problem could be reduced to a sequence of binary classification problems. And so in order to do this thing, we need to exploit certain properties about these atoms. And crucially, we will look at the independence assumption in this graphical model. So one thing we can observe straightforwardly is that if atoms are from different factors, then they are independent of each other given the parent state in action. So by parent state, I mean the state S, not the parent factor, which is S prime. So for example, U and Z atoms are emitted from two different factors. And so we can write that X prime Z and X prime U are independent of each other given S and A, while in fact we can show something even stronger, that these atoms are independent given the parent of one of the factors and the action A. So this is one property we want to utilize. Another thing is that for some problems, not all, we can assume that the factors which are emitted from the same, the atoms which are emitted from the same factor would have some non-trivial dependence. For example, in our earlier figure, this is this shown in the slightly translucent patch is pixels representing a single factor. And this factor, when it's S prime equals to 1, which means it's occupied. So there are two values for every factor, it's occupied or non-occupied. And when it's 1, it could be randomly occupied with some object like a horse or a tree or a rock. And in this case, these two pixels are not emitted independently, right? There will be some correlation. And this correlation essentially means that these atoms have certain inherent dependence between them. And so this would not be true for some problems, and I can mention later about where it won't be true. But it's true, for example, in problems like these where there are some objects which is occupying a grid, and the pixels of an object are not independent of each other. So these together give us sufficient information to reduce the problem to independence test. So atoms of different factors are independent given the S and A. Atoms of same factors can usually be assumed to have some inherent dependence. But there are two main challenges to reducing it to an independence test-based approach. One is we don't know the parent set, right? At this moment, we only can decode the state S, and we have observed X prime. We do not know S prime. We do not even know what parents they are. So we have no information about parents of any factor. And even if we knew parents of any factor, the question is, how do we fix them? And our solution to these two challenges are the following. So in order to, since we don't know the parents of any factor, we can iteratively try all factors of size at most 2 kappa. And then we are rest assured that the parent factor would be in one of these combinations we would try. And the second is that once we assume a set of factors, we can employ rejection sampling to set the values of these parents, because we have a policy cover that will maximize the probability of a given set of factor values. And so we can use the policy cover to reach the configuration where these parents are likely to have that given value. And then we can use the rejection sampling using our decoder to throw away the data where the constraint is not satisfied. So let's take a look at this with more example. So on the right, there is an example which extends the one we saw earlier. And here, our goal is to predict if atom U and Z belong to the same factor or not. So here, U and Z are from different factors. Like U is from S prime 1, Z is from S prime 2. So the answer is no. And so what we will do is, as I mentioned earlier, we will iteratively try all candidates as a parent candidate. So let's say in the beginning, we try S1, S4, and we set their values to say 0, 0. And we also fix the action A. So we will roll in with the policy cover for this configuration. We will reject the data when the decoder says that I have not reached this configuration. And then we will use the data where we collect the X prime, and we'll perform independence test on the pair of atoms. Now, in this case, S1 and S4 are fixed, but S2 and S3 are unconstrained, which means that some non-trivial dependence may leak in between S prime 1 and S prime 2, and therefore between X prime U and X prime Z. And so these can be dependent, and our answer could be that they are dependent. But now we will try S1 and S2 at a different time, and we will repeat the same process. And this time, because S1 and S2 are fixed, X prime U has now become independent of X prime Z. So this time we will declare them as independent. And so this gives the idea that anytime you find a set of factors such that for any value and any action, you always get up with independent, then they are independent.
So can I ask a question?
Okay.
So here,
go ahead.
To perform this rejection sampling, seems like you need to assume a good decoder.
Right. So a lot of our analysis deals with this kind of cascading failure. So the decoder has to be epsilon accurate, and and we use that, and you have to derive kind of.
Oh, I see. So maybe I guess the part that I'm missing, and I think you just alluded to it, is that you can do this in a level by level manner, and you have first have decoder for the previous level, and then you can use it in this procedure to basically figure out what's happening at the next level, and then you use the data to learn the decoder at the next level and so on.
Exactly, because right now we don't have a decoder for S prime.
Right. Otherwise, you could just directly do it in the next level, which would be much more straightforward.
Right. I mean, if you have a decoder for S prime, we can just skip the next 2 steps and just go to model estimation.
Yeah.
So that is the precise point that you mentioned. We use the induction hypothesis and use the decoder from the previous time step to do rejection sampling. Right. So this this is just a in English writing of what we saw earlier. So we will try all candidates capital K, like calligraphic K, which is a subset of this D, which is this notation represents 1, 2, 3 all the way to D, such that the size of the factor is 2 kappa, and an action A belongs to the set of actions. And then we will try to set reach all reachable values of Sk, where K is in kappa, reject the data when the decoder says otherwise, and perform independence test. And it's easy to see that the moment kappa would become the parent, X prime U and X prime Z will become independent. So if there's any kappa such that for all reachable values and action we get independent, then return independent, otherwise return dependent. And so this is the algorithm. It still leaves one question of how do you do independence test? And there's a lot of literature in statistics, but often they are concerned with different issues, like not with issues like computational efficiency, and or you can think about something even more naive, like estimating mutual information. But those things are tricky because mutual information is scale divergence, which are tricky to estimate. And our solution is to reduce independence testing to performing noise contrastive learning. And I have some backup slides, and I can talk about how this is done. We originally thought this was something novel, but then we read some literature and realized that something similar has been proposed in the past. And this works in an oracleized manner because you can use a function class, and this function class can work with very complicated inputs like you would encounter, including high-dimensional images or sound or text. And so this is the approach we recommend for independence test. Any questions so far?
Yeah, can I ask some clarification questions? Not regarding the algorithm, but maybe about this independence testing. So independence is, of course, kind of a binary thing, but when you're going to do testing, it's going to be more like a numerical graded thing. And you're going to incur some errors. And there are 2 types of errors that can happen. You're grouping things that you shouldn't be grouping, and then you're not grouping things that you should be grouping. Which of these errors are more critical? Can you maybe elaborate on what's the implication of incorrect groupings?
So our analysis works with a 0-1 kind of an accuracy for this step, in the sense that we assume all independence tests occur accurately. And because there's only polynomially many tests, by union bound, you get the right behavior. But what's tricky is that, what happens if this is not true in practice? You make error. If I have to guess, I would guess that. Okay, so one error would be, what if you say things which are independent but they're not, and the other error is you say things which are dependent.
Can I ask before that about something about this binary thing? So independence is just this property of joint distributions that it factorizes. So you could imagine a joint distribution which nearly factorizes, and then a test would have a really hard time dealing with that, depending on what test you are using. So I can't imagine that you can have kind of like a uniform bound that says that after so many samples, regardless of what the joint distribution was, these many samples is going to be sufficient for testing independence.
Okay.
So what do we know about this?
Right. So we make an assumption saying that a quantity like mutual information has a lower bound for dependent sets. And so if imagine if the mutual information was greater than beta. So we do assume that there is a margin, that there are things which are not with a mutual information of 10 to the power minus 100. Because those things you cannot tell accurately using bounded error.
Good. This is sort of what I suspected. Where does this appear in the bound?
So say that again?
Where does this appear in the bound, this quantity, this margin quantity?
Right, so it will appear as 1 by beta, polynomial 1 by beta, where beta is this lower bound on the information. So I say mutual information, but what we use is a total variation version of mutual information instead of KL divergence, and this would appear as poly 1 by beta.
Yeah, in the problem statement, I didn't see the beta, but I think it should be there, right?
Oh, right, yeah, we didn't put a beta over there because it's kind of like a problem-specific thing, so it's very hard to just justify it over here. But yeah, you have
Same
it.
Thing as this eta min, I think.
Eta min is the reachable probability. So that deals with the visitation. This is with the dependent. So there will be these quantities, comma 1 by beta.
Okay, sure. To me, they look pretty much the same, but.
Can I ask a follow-up question on this independence test thing? So
sure.
This, I think I have similar questions, but slightly different from Chabas. It's in particular, you mentioned before that you didn't assume a finite atom space, right? So essentially,
right.
And if you think about independence test, you can basically reduce it to two-sample tests, right? Because that's basically what kernel independence test does. You get joint samples and you shuffle them and just decide whether the two are the same.
Right.
But I think without further assumptions, you can't really get a direct an oracle that gives you that kind of guarantees you need when you have a large sample space, right? And usually for example, in kernel to test, you need characteristics kernels. And those things are really non-parametric,
So we do make realizability assumption on the function class when we do independence test.
Oh, that's the part. Do you mean realize say value function or some sort of, or
maybe I can talk about it very quickly.
Okay.
Have some So this is how the oracleized independence test work. It's exactly like you described, that you sample two samples x1, y1, x2, y2 from the joint distribution, and with some 50% probability, you swap them, and otherwise you keep the original sample. And then you predict if the sample was swapped or not. So you have this. So we do it square laws, but you can also do maximum likelihood. And so you do fxy minus z. And then we assume that the base optimal classifier for this problem is in my function class.
I see.
So we do have that assumption. I'm not sure how to feel about it. Like when we ran some basic experiments, that was very true, but it's kind of hard to. I don't know how to like say that that's like a very strong.
I see. No, I think this is better than the kind of, and maybe this is the way you formulate it, but I feel like it's better than assuming like a characteristic kernel kind of thing in the two sample test literature. I was thinking about something else that along the line of it seems to me that I've seen the kind of analysis where maybe if the kind of maybe you're doing something like MMD, and if your function class as discriminators can contain, say, the true value function of the problem, then maybe even if they're not independent and you treat them as independent, it's still okay for your planning problem. I'm not sure if I expressed that, but I was thinking about something along those lines. But I think your solution also seems very reasonable.
Right. Maybe just one more additional point. So this is the base optimal classifier for the contrastive learning problem. And it has, like, you will see that the point-wise mutual information term appears naturally. I guess one can argue that, if your PMI function is like, well, it belongs to like a nice family, then maybe your function class realizability assumption is not that strong. But yeah, so that's all I can say at the moment. All right, so maybe going back to the thing. So using these independence tests, we can tell if atoms belong to the same factor or not, and this gives me the latent emission structure. Now we can use it to learn a decoder. So we have a set of factors. Let's say these ones shown in the dark gray square, and we can pass them into a decoder, which is phi I, and use it to decode the ith factor, which in this case would be s prime 1. So we get 0, 1. Just to be, like say this explicitly, even though we are trying to decode the factors and values, at best we will recover these things up to a permutation in labeling. So my my recovered ith factor might be s prime 1 or s prime 2. The exact value doesn't really matter. So what the actual value could be 0, I could call it 1, and vice versa. So one thing which we showed in a prior work is that a lot of existing approaches that people have tried provably do not work. They may work in some problems, and I think empirically they could be very compelling, but we can construct counter examples where such approaches do not work. Some of them examples are inverse dynamics, where we predict the last action, in this case A, from the last two observations, which would be x prime, which is emitted from s prime, and x emitted from s. And so this oracle has a lot of counterexamples where you can show that they do not have enough information to separate state values. Another thing one could do is to train an autoencoder. So take the observation, pass it to an autoencoder, and recover the value learned by the encoder, and use it for as your decoder. Or one could do like train a bisimulation metric, and so on. So there's like a lot of these approaches which have been proposed. Let's take an example for failure. One of them, say like the autoencoder approach. So in this case, what we will do is train an autoencoder, which essentially is a model trained with this, you can imagine as a funnel-like structure, where it takes a complicated input, projects it into a simplified structure, and uses it to reconstruct the original input. And these models are trained by minimizing the reconstruction error. So this is a reconstruction model. This is a decoder phi I, which we will use to recover the value of the state. And we pass it as input all the bits in the children atom. So this is not the whole observation. This is just the children atoms, which are all these atoms which come from the same factor. The importance of this we will see in a moment. And we, in this problem, make an assumption that these children atoms contain D minus or some M minus 1 noisy bits, which are sampled uniformly. And one bit is the key bit, which contains the state factor bit. So ideally, we will want the decoder model phi I to learn to memorize the state factor bit. But what we can show is that the reconstruction error would be equally good if the decoder was to memorize a noisy bit. So in this case, for example, it memorizes this 4th bit and outputs 1, and then you will get perfect reconstruction error for this bit because you've memorized it, and you can output some random values for the other. And we can also show that if one of the state bits was more probable than the other, then it is optimal to memorize the noisy bit, because then you can always output the most probable state bit over here and output the memorized bit. And so in this case, memorizing the noise is actually the right thing to do. And so this is one counterexample for autoencoders. It's not clear how prevalent this construction would be in practice, but what it is broadly saying is that if the signal in the state of the state is very little, there's a lot of noise, the model might get very good reconstruction error by just memorizing the noise. So instead, what we will do is use another noise contrastive learning based strategy for learning the decoder. And this follows from our prior work. So what we will do is collect a data set with n independent samples as shown. So these samples we will first sample 2 independent transition, which is x1, a1, and x tilde 1, and x2, a2, and x tilde 2. So you can see them over here. We roll in with our policy cover, observe x1, sample a1 randomly uniformly, and then observe the atoms which were emitted by our factor. So that's x tilde 1. And then we do it again with collect an independent transition, x2, a2, x tilde 2. And then the same trick as we saw for the independence test, you sample a Bernoulli random variable. If it's y equals to 1, you add the real transition to the data set. Otherwise, you add the fake transition. So the choice of fake is important here. We keep the x1, a1 as in the real transition, but flip the last observation and replace it by x tilde 2. And so this is shown in the red color here. And we will call this as the imposter transition, and this x tilde 2 as the imposter. And we add this to the data set. And then we will solve the classification problem solve this maximum likelihood by predicting if a given transition xa, x tilde in the data set is real or imposter. And to recover our decoder, we will put a bottleneck model on top of x tilde and this phi, and we will train phi and f on this data set, and the recovered phi hat will be our learned decoder. So one critical difference from the prior work is that we are using the children atoms, which is x tilde, instead of the whole observation, which is x prime. And this difference is very important for recovering the right kind of decoder. Any questions until now? Okay, so we can ask ourselves, like, why would an approach like this work? And so let's look at a quick asymptotic analysis. So in asymptote with like infinite samples and reliability assumption, the model will converge to the base optimal classifier. So it will do us good to look at the structure of the base optimal classifier. So we will look at the probability of observing a real transition, the probability of a transition being real, which is xa, x tilde. And by Bayes' rule, we can write it in this form. And so this Bayes' rule, and we also assuming that py is uniform. So the py term would cancel out. And so this is the probability that xa, x tilde is a real transition. And this is a probability that xa, x tilde is a fake transition. And now observe that the real and fake transition have the same marginal distribution over x and a, because we use the same x1, a1 in both of them. So we can cancel out the pxa from numerator and denominator, and we will left with the probability over the x tilde. So in the real transition, the probability over x tilde is nothing but the transition probability, because that's how you get to x tilde from going from x and a. But in the case of the fake transition, the probability of x tilde is the marginal probability, because x tilde 2 just comes from a different transition altogether. So this could be expressed as this rho, where rho is the marginal over x tilde. And now we will apply our factored block MDP assumption. So we know that the x tilde is only the set of atoms emitted by some factor s prime I. And we have the block MDP assumption on this factor. So we can take out the emission probabilities, leaving only the S prime I inside the transition function, right? Because S prime I is the decoded, is the actual value that emits X tilde, and Q is the emission probability. So this will again come out from the numerator and denominator, and we can cancel out the emission probabilities. And we can do another simplification that the value of S prime I only depends on the parent value. And so this is the simplified form of the base optimal classifier. And a quick observation tells us that this only depends on the value of the factor S prime I and not the whole state S prime. And so once we learn the base optimal classifier, there's no reason for us to separate observations which come from the same factor value, because there's not enough signal. There's no signal to separate them. This also motivates why using a bottleneck construction over here allows us to still claim realizability, because this phi maps X tilde to 0, 1, and this X tilde is only dependent on the 0, 1 value of S prime I. So we have realizability even with a bottleneck. And in general, it can merge. So this base optimal classifier can still merge factor values, but we can show that that merging is benign for the purpose of exploration. But if we do want to get the exact state decoding, we can assume a margin condition and recover the exact state, like we did with the independence test. And this margin is trivially satisfied for deterministic and near deterministic problems. So any question? Okay. So now we are almost done. So we have recovered the latent emission structure, and we have also recovered the decoder, and we can use it to estimate the transition dynamics. Just making sure there's no. So the way we will estimate the transition dynamics is by first estimating the parent set. So we can learn this transition function shown over here for all values of I, capital I, J, and A, where capital I and capital J are two set of factors of size at most kappa. A is an action and I is some factor. And we will view I as a candidate parent set and J as a control set. And now imagine that if this transition function was learned to good accuracy, and if I was the parent of I, then changing J or changing the value of Sj is not going to affect this transition function just by the Markov assumption. And so we can define the parent set as the value of I such that the transition function is least affected by varying J or the value of Sj. And once we have the parent function, the transition function for this factor and the overall transition model are straightforwardly given from the factored MDP assumption. So just one more comment here is that in this case, we don't really need to recover the parent set exactly, because like we mentioned with the earlier two steps, there could be a parent which is almost not a parent, like which has like some microscopic influence on the evolution. And if we care about the only the accuracy of the transition model, like something like a simulation lemma, we don't have to then recover this parent, like approximately parent. So we can the parent set is not recovered up to exact accuracy, and this saves us a margin assumption over here. And so this mostly completes the factorial algorithm. Once we have the transition dynamics, we can use a planner to recover the policy cover for all possible combinations of the new factors. If a combination is not reachable, then we won't add the policy to our policy cover. And once we have the policy cover, we can now jump to the next time step and repeat the process. One small comment on this planning aspect is, is that the planning in factored MDP is EXP time complete. So it's significantly hard in general. However, there's like 2 decades of work on doing approximate planning strategies in factored MDPs, For example, you can look at the work of Carl Gestrin, Jeff Gorton, Daphne Koller, and others. And so these methods use like linear programming and approximate dynamic programming kind of based approaches, and they can show that planning is often, like approximate planning is often possible. So in conclusion, the contributions of this paper include a new model setting that for the first time combines the two real-world challenges of rich observation and factored state space. And we argue that these two problems occur simultaneously in many real-world problems, but people have been studying these two trends separately. And the challenge with that approach is that the algorithms designed for one challenge do not elegantly generalize to the other challenge. And so there is a need for studying them together. And we make like a first dent in this direction by proposing a new approach, new setting called factored block MDP. And we propose an algorithm called factorial, which solves a subset of factored block MDP. And we get a sample complexity which is polynomially dependent on the number of state factors and only logarithmically dependent on the number of atoms. This log dependence comes because of this pairwise independence test that we do. And it does not depend on the complexity of the atom space, which could be arbitrarily complex. And it works by reducing reinforcement learning to essentially performing multiple noise contrastive learning, which is a well-studied representation learning approach. And so this is kind of nice in the implementation sense that one has to use the same Oracle call again and again, so it kind of makes it easier to implement it. And the algorithm is computationally efficient anytime an approximate planner is provided. However, this is not going to be true in general, and that begs us an open question to which I will come on the next slide. And as I mentioned, is agnostic to the space of atoms. So we'll conclude with some open questions. So I would just say like there's a lot of gap between theory and practice, and this is like just the start. And like even this factorial algorithm, we cannot really apply it to any real world problem just because even a dependence on the number of parents in the exponent is actually quite a killer when it comes to complexity, like computational complexity. And going forward, how do we remove these assumptions, or what assumptions would make planning possible, are like some natural questions, because like it's kind of nice to have like tractable problems where the planning is like just provably polynomial as opposed to working with approximate planners. And also like what assumptions can we do to get the polynomial complexity polynomially dependent on the parents as opposed to 2 to the power number of parents. And there's also some other generalizations that one can think about is that, as I think Nan mentioned, that the parent factors are fixed. And this doesn't work when the factors are objects, right? So if you think about different cars on a road, and if each car is a factor, then the neighboring factors are changing. So you're not going to always have the same parent factors, right? And so how do you do this dynamical parent factor assumption? And this also goes for the children atoms, right? What if the pixels emitted by the factors are changing position? They emit like on the left and they emit on the right, and so on. So these generalizations and assumptions are needed to further reduce the gap before we are able to apply such algorithms in real world. So everyone, thank you. Okay, just over time.
Yeah, so I had another question, and Chaba also generalized it quite a bit. So I guess the general question is, what parameters your algorithm need to know in order to run? For example, so some of them I can imagine, for example, like, do you need to know the upper bound on the number of parents? Or like for that one, I don't know if like something like doubling can solve the problem. The one that I was curious about is again related to this independence test, because when you take that, when you need to solve that discriminative learning problem, it seems like to know whether the two samples are independent or sorry, the two atoms are independent or not, you need to know the base error rate for that prediction problem.
Right. So these are the so there's quite a bit of hyperparameters we do assume. Let me just tell you one by one. So kappa is it's either an upper bound or it could be the exact number, but upper bounds never hurt on the number of patterns. D is the number of factors. I'm not sure where you use D. I think it may appear in like setting some a value of some sample complexity.
Yeah.
Beta min is the lower bound on the information needed to do independence test. Eta min is the reachable probability bounds. So I think both eta and beta min. So I would say these two dependents are somewhat harmless, if I could dare to say that, because they are only used to set sample complexity bounds. So which means, and like even though we write these things in practice, like no one ever, like in practice, people don't really set those bounds like the way they're written. So in general, like eta and beta would be like free parameters that people would try. And the idea is that as long as you are being conservative, like you use a smaller beta and eta than required, things would work. So they only need to satisfy like one-sided inequality. Yeah, so these are the parameters. Delta is the failure probability. Not sure what sigma is on top of my head. Yeah, but those are about it's about 1, 2, 3, 4, 5, 6 hyperparameters that we assume.
Yeah, I guess can you go back to your extra slide for the independence test?
You mean the
extra, the backup slide. Yeah. So for this one, if loss is greater than tau.
Yeah. So let me. I actually show you in the paper. It's very it's much clearer there. So this is the and I mean this section is written in an independent fashion, so it doesn't refer to the rest of the paper. So we assume that there's a dependence of beta on the information, and so the tau is this. So 0.25 beta squared by 1,000. So where beta is the mutual information term.
But I guess the question is, does the algorithm need to know the value of beta, and does that beta changes? You're running many different independence tests, right? Like, seems like the beta can change from one test to another, and also does your knowledge on this beta, is it one-sided or two-sided?
I see what you're saying. You're saying like, I mean, can I just always use a smaller beta than?
Yeah.
I mean, I would like to think that I don't need the two-side, but I am not like super confident right now because there might be some step. Xinghua, do you have a sense at it?
I guess my high level intuition here is that you're making a prediction problem, right? And you said that it works when you have like realizability type assumptions. My immediate thought is that basically you want to know whether the empirical risk you see is close to the base error or something like that, right? But then it requires you to know the base error rate in the first place, and that feels like a two-sided thing instead of one-sided thing.
So I mean, we don't really need to. Okay, so this is all what we need is the beta and then the upper bounds. This works, and I'm just thinking that if the mutual information is greater than beta, then it's also greater than any beta prime, where beta prime is less than beta. I just think that the smaller beta you take, the more number of samples you would need. And so that's what motivates me to say that you need one-sided bound. But I'm not like 100% sure because there might be some step where, this thing could be a little bit tricky. So I don't want to like say it with like complete confidence, but my hunch is that it's one-sided.
Yeah, because if they're independent, it will be
zero,
very close to 0.25. So basically, you only need to make sure Yeah, so the concentration error is not large.
So right. So when things are independent, the base error is 0.25, and what this is saying is that so this is like the threshold.
I see. So beta is basically, I see the beta is really like a kind of like margin kind of thing. I guess the part that I wasn't sure about is like is that 0.25 is like it's actually a constant. I thought that number could change from problem problem, but it seems like it's actually a constant number that you already know.
Exactly, it's constant because independent. Okay, so what's going to happen is that when things are independent, my f star is half, right? Because if you look at this problem,
right?
here,
So it's your error rate is just 0.5 square, which
0.5 square,
yeah,
exactly.
Yeah, right. I see. It makes sense. Yeah.
I do have a question, somewhat general. You said that the algorithm is computationally efficient, but I think that this is subject to assuming that a bunch of things are computation, not just the planning part, but for example, the noise contrastive learning, is that necessarily computationally efficient?
Right.
I also, yeah, go ahead.
Right. So noise contrastive learning, I would say, is like the most common representation learning approach. And so it's like routinely done in practice. And there's a lot of like things on how to make it parallelizable and converge. And so there's like this is like a lot of like work in empirics. I would say like even 20% of empirical papers these days are like just noise contrastive learning. So I would say the noise contrastive learning is quite easy to realize.
Sure, but still the precise statement would be subject to that someone is able to do that. I mean, I can cook up examples maybe where this is also hard, or I'm not sure whether I can do that. But
what I can do which is hard is this bottleneck thing.
Yeah.
So once you put a bottleneck, things are no longer nicely convex, and even like there are some deep learning tricks to optimizing it, but this does become tricky, and there are ways in which this could be dropped and some clustering technique could be done, but then you pay like 1 by delta in failure probability as opposed to log 1 by delta. Because you use Markov inequality, and then you start going into this brittleness regime. Yes, I would say like this planning and the this fee is kind of not desirable. I would also say that the fact that our independence test just kind of like blindly tries all combinations is also like it's easy to implement it, but it's very frustrating to just like wait for those results. So they're kind of like not like they're polynomial, but the degree is high and like empirically not like nice.
Okay, I was also curious about whether you have some sample complexity results for this noise contrastive learning under some settings. It seems that you're maximizing over some classes, and so
that I can so if you like learn a decoder F, let's say so in this case, essentially your guarantee would be the following. I'm not sure if you can see my LaTeX.
I'm seeing as you're typing, and if you will LaTeX it, then we will see the formula.
This comes from like Hofstein-Bernstein, but it's a Hofstein-Bernstein bounds.
So you're gonna say that let these sets be finite and then apply a union bound, and
yeah, but you can
so it's basically empirical risk minimization or whatever maximization.
Exactly how this is.
I see. Okay.
Right, and this could be generalized to like Rademacher and
right.
Kind of,
so it's gonna depend on what is this decoding set, and okay, that was basically my question. That you're gonna have some measure of the complexity of the space in which you're searching for the decoding functions, and that's gonna show up. Okay.
I don't know. For some reason my LaTeX won't. But you know, like, I mean, I'm just like gonna write the standard.
Right. Oh yeah. No, I got it. It's fine.
Right. So yeah. So that's the sample complexity bound.
Right.
That we will get.
Interesting. And I guess here the point is that you are avoiding learning the details of the emission kernel.
Yeah. So I mean, we don't model. So that's one good thing about the noise contrastive learning is that it doesn't require doing generative modeling.
But would the sample complexity be higher for that, by the way?
So it depends on the complexity of the function class that you're using.
Yeah.
There is empirical evidence in some problems that noise contrastive learning is lower sample complexity than generative modeling. So, for example, in language modeling regime, there are these approaches like BERT, which are generative modeling based, and there are approaches like Electra, which are, you know, or Word2Vec, which are binary classification. And the latter strain significantly faster than the generative modeling. So you can actually.
Do we have a theoretical explanation for why and when that would happen?
But I mean, one can argue. Okay, so maybe like one reason to argue, which is I don't think it's like right, but is that if you look at the Rademacher bounds for neural networks, they involve multiplication of weight terms and weight matrices. And in generative modeling, you have this giant weight matrix, which is projecting over like 100,000 tokens. While in noise contrastive learning, you just have like a 0, 1. So you're like, just doing a dot product and taking a sigmoid. And so if you just probably compute the Rademacher bounds, they would be like smaller for the noise contrastive based models. But since the Rademacher complexity itself is like vacuous, I wouldn't really treat that as an honest reason. I would just like show these examples that if you look at these Electra based approaches, which are contrastive learning, they are much more sample efficient than all this like other approaches.
But maybe that is, it would be nice to see some, I don't know, sharper theoretical justification for this. I don't know. At least for me, it would be.
No, I agree, but I wonder if this requires like solving like deep learning generalization theory.
Yeah. Okay. Yeah. So one way of testing that is think about things like tabular setting. So how would things like there? Everything is realizable. Everything is under control. You can get results with both methods. And then if you see a difference there, then okay, you got it. If you don't see a difference there, then there is something that is more mysterious, or like relates to how things are represented, and then maybe all bets are off. So have you looked at this?
No, we haven't. Yeah, maybe. I mean, if you can represent things from linear model, maybe some
things like that,
more compact and precise theory could be said. We didn't really look at it because, like, at least in my view, like noise contrastive learning just empirically works, and I would like use that as the like test. So it doesn't really like so I don't really like haven't really thought about that like analyzing it because the empirical evidence is just so abundant.
Okay.
Yeah, maybe like that's like not a. I do agree that there's need for understanding these things theoretically. I just haven't spent any time doing that.
Yeah, sure. All right. Maybe we can stop the recording and then thanks again.